It is a classic of everyday life. To remove the cable from the laptop from a backpack and find it made a knot, even if no one has touched it. The same happens with the headphones, with a thin chain, or with any cord stored in a drawer. The entanglements seem inevitable, fruit of chance and reduced space. But in the world of molecular biology, knots also occur and can be fundamental to life. If you like this type of content, don't forget to subscribe and like the video so you can be aware of more fascinating research on science and its impact on our daily life. Your support is very important to us. A recent research published in Physical Review Letters provides an important key to understanding how these knots are formed in biological structures. A team of scientists from several universities demonstrated that a single semi-flexible filament can be knotted on its own as it falls through a fluid, without receiving external disturbances. This finding opens new doors in the understanding of molecular biology. The fact that an isolated filament can tie itself has been an unresolved problem within the physics of soft matter. It was assumed earlier that in order for something to be entangled, it had to receive external intervention. However, this study shows that it's not always necessary. The researchers used computational simulations to study how a semi-flexible filament behaves by falling through a viscous fluid. They observed that the hydrodynamic flows of the liquid can deform the filament, generating loops that cross and block, forming stable knots. This is a dynamic process that evolves into more stable configurations. One of the most relevant aspects of the study is the combination of physical variables necessary for these knots to form. Gravity drives the downward movement of the filament, while the type of fluid must be viscous to generate stable flows. In addition, the more flexible filaments tend to form knots more easily. The simulations allowed to observe configurations of knots that not only remained stable, but persisted for prolonged periods. This is crucial on microscopic scales, where small disturbances can alter vital structures such as DNA. This study not only explains how knots can arise under specific physical conditions, but also provides a framework for better understanding the behavior of biological polymers. Knots in DNA can have varied effects, from functional to harmful. Beyond biological implications, this finding opens doors to new technological applications. It mentions the concept of knot factories, devices designed to create knots in synthetic materials accurately, which could revolutionize the way materials are designed. Knot control could be used to create materials with specific properties, where the internal structure is determined not only by chemical composition, but also by topology. This could have applications in industry and in laboratories. One striking aspect is that the knots achieved in the simulations did not require long filaments. This suggests that even short polymers can reach stable configurations, which has implications in laboratory experiments and in the connection between theory and observation. This study offers a rigorous explanation of how nature can generate order and complexity from simple movements and universal physical laws. Thus, even if it does not solve the mystery of entangled cables, it gives us a fascinating perspective on the world around us.